So, welcome, liquid printing station.
You know what I really loved about your lecture today?
About?
Your analogy with the honeycomb and the bees. I really love that part.
I always make a lot of analogies of everything. Like,
I know, and I also really love that you do little drawings.
I don't think technical things needs to be explained difficult way. Like, there are a lot of analogies they can do everywhere.
Yeah. Sure.
Okay, welcome to the most messy, annoying process, but with the best quality and surface finish. Estoy yo. So, this is what we consider like liquid printing, SLA printing, LCD printing, DLP printing. Let's explain a little bit the differences. They all start with a resin that I don't have the pot right now, but usually it's a pot just like this. That comes in a plastic bottle that is UV proof, so you never get to see the resin. Why? The resin solidifies with UV light and UV frequency light. So that means in the moment it has light, natural light, it will photo-initiate. So it's a base print material that has some photo-initiators. It's in some chemicals that actually they create and initiate a chemical reaction that creates the bonding of the material. So, for example, lights, even artificial lights, they also have some kind of UV frequencies. They produce a little bit of spectrum of UV. So it's a material you always need to keep in the bottle. It's a material that is sensible and has a due date. It means we cannot keep a bottle of photopolymer resin for 2 years and expect it to work. It just will not work properly and not with the same characteristics. So usually the due date of the resins is around 6 months maximum.
What do you use this type of material for?
So this resin is when you want to use for really high quality prints and some high detail and small surface finish prints. Usually you find a lot of these prints to create, let's share the screen. Really high detail and integrate designs like this, or like, for example, it's widely used to create mini figurines. Actually, like all the model makers, they love this machine because it can create really high end detail, like these ones. It's widely used for creating also jewelry. Actually, for example, right now, like most of the jewelry designers, just go. For example, Jessica is a famous like jewelry designer. Yeah, it's actually produces a lot of pieces of jewelry using this technique. Let's go to the shop. Like earrings that are designed like this. There are really complex and intricate designs that could not be made by additive manufacturing techniques. So how does this work? This process works by, you know how jewelry is made?
Yeah.
So they produce a mold and then you cast the material on it. So in this case, what you use is a certain type of UV photopolymer resin that is wax-based. So you print your model, let's say this, and you cast in plaster. Then you heat up the plaster, the wax melts, and you have the empty of the model. And then you can cast gold on top and fill the space. So you can create really high and intrinsic designs to a resolution of 0.1 millimeter. Like the definition of this machine is really huge. What are the bad points of this kind of machines? First, let's stop sharing the screen. I want to show you for a second. So first is you don't need the machine per se. You need a lot of side machines. For example, here you can see right now. Let's move the. We have the first one This is the LCD printer. These machines are usually constrained by the print size. The print size of this one is basically the size of a phone. Exactly the same size of a phone, because actually they manufacture phone screens for parts of the machine. We have some always to clean the parts when they come out of the resin, because they are deep into a resin and they come with liquid around that still hasn't solidified. Then, if you can have it, you have an ultrasonic cleaner. That is a mechanical ultrasonic cleaner that prints with alcohol the resin. And then we have a UV curing chamber. All these printers, when they photopolymerize the resin, they don't harden completely the resin. They keep it in a semi-hardened state, but not to the end of the material capabilities. Why? If we harden completely the resin, we will not be able to take it out of the machine. As simple as that. So usually what you need to do after you produce a part is you need to post-cure it. You have this machine that basically is a box with mirrors and UV light sources. That in this case is like neon UV LEDs, neon UVs lights. That is like a microwave of light. And you keep the model hardening there for X amount of time. That will depend on the resin you use. Resins, there are a lot of types. There are hard, there are semi-flexible, there are acryl-based, epoxy-based. Most of the resins for SLA printing are acrylic, the same as you use in the laser cut, acrylic-based. So actually they produce strong and tough parts, but brittle. So for example, this model is 3D printed. Well, can you later show on the camera? This model is SLA printed, is solid, but the edge is broken. And you can see that it's really shiny on the broken edge. Why? Because acrylic breaks in a brittle way. But I can show you, these are some samples. So this, for example, this is the worst quality finish that we can have in this machine. As you see, the quality finish in this one is amazing already in the good one. It gets like almost super perfect finish edges.
This was done in a mold.
In a
mold.
No, on the machine directly. Also, these machines usually are slower than FDM printers. There are some type of this kind of technologies, for example, carbon brand SLA printers, that they have improved the speed by 10 of normal printers, but they are quite expensive, those ones, and they need a lot of maintenance.
But this was done with a liquid substance.
Let's go. We have a sample. We will do all the process.
It looks like a big wart, so you don't dry it correctly or the material wart.
Yeah, exactly. The part of SLA is really sensitive on how you manipulate your part, meanwhile it's not completely hard, and how you locate your part. The tricky part on the SLA print is actually to make the print stick properly and print properly. Let's go a little bit on an example. This you have here, for example, this is a Photon S LCD printer. This is a Chinese, the new generation of Chinese resin printers. It's affordable, it's nice, it's only like in the $500 budget. And the print quality is good. This is, for example, is the one of the first generation. We have Form 1 and Form 2 that, I'm sharing my screen. No. The one that we have here, why I don't see myself? The one that we see here is a Form 1. This one is a SLA type printer. It means we have a laser, that the size of a laser is really, really small. In this case, it's lower than 0.2 millimeter, it's 0.01, I think 0.05. That basically we are moving really fast to harden some parts of the, we are like light drawing, like painting with a laser on the surface. In this case, we light up the whole surface at once. Let's explain a little bit the difference. Oh, this is perfect. So we have 3 different types. SLA, a laser with some mirrors that they move fast and move the laser on different areas. DLP is a projector that projects the image black and white, being white light, being black no light, with the shape of the slice, and LCD that they use the same technique, but in this case we have a light source and we have a LCD screen, the same as you have on your phones, like similar, not exactly the same, that basically when you show a color, black, they hide the object, and when they show white, it means the light passes through. So it creates masks. Like it will be like a silk screen mask, but of light, and they do it really fast. In here, it's important the layer height speed. How fast it takes to harden the resin depends on the technique and depends on the resin too. Some resins are faster than other ones. The average layer height resin speed is 1.2, 1.5 to 6 seconds. Imagine that you have like 1,200 layers by 6 seconds, the amount of time it takes to produce. For example, that big print takes 9 hours to be printed. Also, this is deeply influenced by how you locate your model. In case of LCD and DLP technologies, it doesn't matter if we are printing the full surface or just something, because we are lighting the full layer at once. We don't need to move anything. We just can light all the layer at once. So we can fill the platform and it will take the same amount of time that we just print something that is really small. What makes the time difference? The total amount of layers that you need to print. That is going to be the total amount of movements that you need to do, because this machine, they don't have mechanical movement parts. They only move the set up. They work the opposite. They have so this is a form one, and we have the resin bag. In this case is clean, we don't have resin. That this is a building platform that is not acrylic box, has a Teflon, so actually it doesn't stick like your fried pan. And we put the resin on top. And here we can see the mirrors and the laser. Well, we see one mirror, and the laser just is protected. We have the platform that moves down. And start printing. We harden the first layer, it moves up a little bit. Harden the second layer, moves up a little bit, and that bit will come up. Actually, it's quite magic because the print appears coming out of nowhere, just the resin. What happened? In general, these machines are prone to fail on the first layer, on the beta version. And what happened? The material is also there. Actually, we don't see that the model has failed up to half an hour later of the start. So it's a little bit of a gambling the first half an hour. Then maybe your model has failed. What happens if it has failed? It's not sticking here, so the model gets stuck in here. And what's happening? You are hardening and hardening and hardening and hardening. So what happened then is it becomes really messy. Is you need to start fishing your hardened model in the side of the resin. Let's go a little bit on the right side. Everything has come up properly. All these resins, they have a lot of dilemma on how toxic they are, especially when they are not in the hardened status. So there are a lot of studies, depends on the manufacturer, if they are more or less cancerigenic, but I will say that it's almost the same as like staying behind a car. Like we have considered cars as normal, but they are super cancerigenic in general. So always recommendation is not only because it's a messy process, but use gloves and also have a lot of toilet paper to throw it because you will need a lot. So let's go over the steps. We just sent to print something here. Let's see how we take it out. So first thing is we set up. Can someone control the camera a little bit, please? Like we can do it. We have zoom out, move the camera.
Exactly.
Yes.
So if this takes 9 hours to print, have you guys ever measured like how much energy it requires? Like I'm wondering if it's
The energy consumption of 3D printers depends on the 3D printer, but this one is really, really low. Actually, it's easy to calculate because all the machines have power supplies. So for example, this one is 24 volts, 2.5 hours. If you want to make the here, energy required for 3D printing is watts to DC amps, DC calculator, like clear drawing. No, it's the but there are calculators to see the amount of watts of energy consumption per hour. But more or less, FDM printer, I can more or less, depends on material you print, because depends on the temperature range, but you are around like 200 watts, 300 watts per hour. So let's say we have this camera, please. So they have a cover. Why these machines have these covers? Because they are like UV filters to protect the resin from hardening. More zoom.
Even more, wow.
More zoom. Yeah. So in this case, for example, we have the resin bag that is here. We have the platform. The recommendation is always take paper because it will make a drop. They all have a holding system. This one is a screw. This one is a lever that we move it. So you see the first, we always have drops coming out. And right now we printed this model. And we will clean a little bit. And then we can put it on the table. So right now here we have some samples of 3 nozzles for the base extruder that we printed, and we have lots of supports. In this case, we printed 3. It will have taken the same amount of time to print 9 than 1, because we only have this layer height on the side. I will move this closer to each one of you so you can see. So right now, the print is full of supports that we want to take it out.
Why is it rotating?
Why is rotated? It's because you cannot print directly on the platform. It will deform your print.
This is the one you showed us in the movie,
No.
So if you print in resin, you have to rotate it.
You need to rotate. And actually, there are programs that it will automatically produce. Printing in resin needs, like most of the time, you support for it. So these machines are really sensible, and we are talking about resolutions of 0.001 to 0.005 millimeters. That means they are really sensible machines in general. The bed, in this case, we have some holders. You can see I cannot tilt a lot because we have the traditional liquid state, and we have the flexible surface on the bottom. Can you see?
Yeah.
So always something that's really important is shake your resin before printing, and shake the resin before printing. The resin is a mixture of different chemicals, and the photoinitiators tend to go lower on the so you haven't used for a day. The photoinitiators are not correctly mixed. So it's really important to shake, and also the temperature. This is not really clean. The temperature is really important too.
Of the resin.
Of the resin, like it needs to stay at like a 25 degrees at room temperature. Needs to stay at that. All the mixes that you can see here, are alcohol. Most of the resins are cleaning with alcohol, like ethanol. Some resins can clean with water, but most of them they clean with alcohol. Right now, I'm just cleaning this one. I don't know why, but this is not supposed to be dirty. This is the screen. With the resin on the screen, it will keep there forever. Okay. As you see, I just started on the amount of paper. That is. So you see the back. Something that is important is you cannot feel completely the back. So it depends if you're printing like really volume and a lot of material, you will need to think of refilling the tank while it's printing. As easy as just the print is printing, just come with the bottle and fill a little bit more. Thank you. So in this case, never use a metallic spatula. This surface is flattened with the CNC and you will break it. So always use your finger to take the model out or a plastic spatula. I will try to take it with my finger. No. Oh my God. I need to go for the plastic spatula.
Yeah, I still don't get how it actually works.
I get it how it works.
Yes, I don't get like how it makes it like from the liquid stage to the stable.
My
Like,
question
stage.
is,
I don't get that.
what's the difference? Now you're gonna see.
Yeah,
Because of the light, the laser.
what the laser is like because of the heat it produces, or
No, it's also chemical reaction.
it is the reaction.
But
Like,
the liquid that enhances the light and the liquid coming out.
Hello.
It's reacting to like UV light.
I don't know what it is.
The polymers of one.
No.
But I just wrote a little bit the supports.
Okay.
yeah, bro.
So for example, right now, this should have gone a little bit easier from the model. So that means the curing time was not properly set in the machine. Curing time. We can set up, one is the layer height, another one is the amount of time spent in the layer on curing. Gracias. So, yeah, I just wrote the supports. You can.
Can I touch it or do I?
If you clean your hands later. So when you have your print object that is dirty and ugly, you can use this back. Clean it first.
Is it water and alcohol?
Ethanol.
Ethanol, that's right.
So we have 3 bags here. You see one is cleaner than the other one, the color. Just drop the object and flip it. When we just make the first clean, we just put it. Take a cleaning time. When we have finished, we drop it in the other one that is like a fry.
I know, but like.
And we have timers. One is temperature, another one is like time and intensity of the ultrasonic. It's quite arranged in the sound. So usually in the temperature we just set up the average, like room temperature, like around like 30 degrees to make it a little bit faster. And the stand we just put at the maximum. It's quite annoying.
Is the ultrasound interfere in any way the structure of the resin?
No, it's by microgravity sound. So you keep it here cooking for a while. And when this is finished, that what we can do is we can launch the program. And then we open this. We put the object on the platform. Camera.
Yeah.
So it's like a microwave of mirrors that we put the object on top.
What is it called, this machine?
Huh?
What is it? Is it just
UV curing time.
it is heating, or what is it doing?
What is the purpose of this?
This has lights, and
Yeah.
mirror reflects the light all around. So basically, like hooking or fill with light.
Okay.
And we have a timer that is coming somewhere here, and a button. We have set up the timer to be like 45 minutes. That's quite a standard screen time. Some resins need more time than other ones. What happens if you overcure? Depends on the resin. For example, this one that is transparent will become yellowish. Imagine what happens, for example, with plastic and sand, like a surfboard. Like all surfboards, they look yellow because plastic tend to like degrade with UV. UV degrades all of the objects, like even your skin. So basically, we are over degrading it with plastic. It's mostly aesthetic, but it's important. Especially, yeah. Exactly. This is solid gypsum. Most of the time, SLA or like UV technology, you need solid gypsum. What you can do, what happens? You need to leave a hole so the liquid can get out on the last layer. So your infill doesn't become fully liquid. You are creating a chamber. If you close the chamber, the resin will stay there inside. Well, you will have your only solid object and liquid moving around your. If you create, it will harden. But let's say the point of making like hollow objects is to save material. You waste material inside, but you leave a little space so the liquid can get out in the lower part of the mold. So with a finish. And now, my recommendation is this process, the resin is flexible right now. I can, if I leave my resin, I leave my fingerprints. So what you do is you with some tweezers that I don't have here, you break up the supports. Breaking the supports now is easy. After curing, no. So this is really small. It's the worst print I could show you. But
Is it water in the ultrasound bag?
no, alcohol.
Alcohol.
How do you know when you're designing where to put the support system?
They support automatic. They generate automatic.
Oh,
So you take the support out completely, and then you put in the bag so you avoid your fingerprints. Ideally, this could have done before. I will do it here. I don't care about fingerprints right now. And I usually use soft sticks or something to touch the less amount possible color, or some tweezers to hold it with some pollen that I will get to see. Huh? You will always see your fingerprints. And you put it in your mouth and cook it.
and this is just on off.
On off and time.
On off and time.
Yes. So here, in some area, I don't know now, but where, but here in this one, I remember that I left my fingerprint somewhere.
How much time do you need to put this on?
This is going to stay like half an hour. So how to make the file?
Because it's
Box. For this one, we don't use Cura, we use specific like software for SLA. But in this case, LCD printing. That basically we have the surface, the model, and it allows us to move the model around the surface. But what happened? For example, the biggest and most difficult part here is this one. You see this? This object is hollow. It's a cylinder. Think that we are sticking a surface against another one with a cylinder. If we need to unstick from the surface, we are basically creating vacuum. This effect is vacuum suction between both layers. This is a cylindrical object. So this creates more vacuum here. because the air cannot get inside. What happened? The model will get stick to the base of the resin. So we cannot create vacuum with our models. So how we locate this model? In a way that reduces the amount of vacuum as much as possible.
That's why you do it.
Uh-huh.
But it's like a structural problem.
No. In this case, I care about this thread. So I will try to rotate it in an angle that will not support the support of my thread. Then we have the support. In here we have light, medium, and heavy. Depends on the part. Bigger models usually need bigger support, but also depends on your model. And this one, sorry, I cannot tell you like there is a golden rule. This is about knowing how your machine works. And this one works different than this one. They have little tips, and it's about knowing if the model, the orientation is good or not. And usually we don't need to touch this. We just generate all, and it will create automatically the supports. The good point is, for example, here there's no support, so I can add another one. And you can erase or put a support in a support, etc.
But the idea is try to put the model to have more than possible support.
Yes, but enough. In SLA, it's not decided. You need supports mandatorily because your model is in the air most of the times,
Okay.
but the less amount of support possible. And we have the material selection. That in this case, for example, is we have all these options that is make the model hollow. Or this case is auto layout. Let's erase the supports, remove all. Let's go here and auto layout, center. This is, we have several models, it will keep space between the models. Hollow, what is the wall thickness, the precision, and the precision is to the outer or the inner wall. Let's start and let's see.
What is the biggest size it comes to?
In this one, I don't remember right now, but I think it's 100. So,
I don't mean like a lot of people can have that.
Dimensions of no, platform. I think it's 180 by 160 by 180.
So when the supports come off, they don't leave any marks?
They leave a little bit of mark. That depends on how you set up this contact shape. The contact depth is 0.4 millimeters and 0.8. So at least there's a little less than half millimeter on the contact. Depends on the sort. You always try to avoid where you put the supports or etc.
And it's the same material, but it's just super thin and it breaks up.
Exactly. So in this case, as we are working with usually small and detailed models, you are careful. You do it with some tweezers and a little cutter knife to cut on the edge. It's a little bit like model making. Big hole, for example, in case you want to hollow, you need to put a hole somewhere in your model. In this case, for example, the hollowing is wall thickness. This model is not good for this at all. And repair model. Then we slice. Let's launch a file. I usually don't have files that small. Of course.
I think you like bunnies.
Yeah.
No, this is Stanford Bunny. This is the standard test for 3D printing until 2014. Because you're I'm not making it up. Like
No, it was a joke before last time we saw bunnies.
yeah, because this is what we consider the standard 3D printed test because has overhang angles, have high definition on some areas. So it's the same as the Benchy test.
So visual.
Benchy test. I like the bunny more than the Benchy. You have the Benchy test. These kind of models, they have like all the things that can test the printability and quality calibration of the printer. So actually, when you calibrate, make a printer and you calibrate it, you make this one or the bunny. Usually now you make this one because it's more efficient. So you test all the qualities and you can see overhang angle, stiffness, like breaches in just one model. That's the reason. Like before it was this one, this is called the Stanford bunny. So you make it hollow, inner, and you can see now, for example, that it's following your model completely. What happened? Right now, the liquid has no space to go outside, so we need to dig a hole somewhere. Add a hole. I don't know. Somewhere in the model, so we can actually put the resin out.
That resin becomes waste, or you can reuse it.
This one, it stays in the bed. But I just made it here like randomly. Yeah, you will want it here at the last part of the model because the model is rotated. Yeah, I always need to think that this model is rotated. So when you have done this, you slice, and what you have here is what the machine will see. Actually, in this case, is the layers. This is the mask of light to print the different layers. And this will take, for example, 5.5 hours.
How much?
5:40 minutes.
What size kind of resin?
The entire body.
Wow.
Yes. Yeah, there's lower, but it's what you have. Yeah, it fits. Oh, it fits right now. Good. It's orientation. Apart from that, actually, the programs are easy. Like there's nothing much to play. It's just about calibration of the resins. Calibration of the resins is, I just have it to save. Settings here. Is, for example, here, you need to customize your resin. And this one, you do it based on the manufacturer settings for your machine. You have the resin density is 1.1. This is more or less $30 a liter. And the print is what matters. For example, here is we have layer height. We have the layer height. Right now we are printing at 0.04 millimeters each one of the slices. The bottom layer count is the first layers. With the first 5 layers, it's going to have a bottom exposure of 60 seconds. It means the first layer, 60 seconds, second layer, 60 seconds. So they have more time to harden, so they stick well to the surface. And then the other ones, we just harden 8 seconds. And this, a recommendation is try to stick to the manufacturer's setting for the resin. And if not, look on the forums. Like a lot of people share the settings and values for the different machines. Actually, I think I have a link here of machines. And cubic photon resins. For this machine, there is a group of users of the different types of manufacturing resin, speeds and value. I just found this in a forum of people and who has like actually tested the values and some tips. For example, print really well. This one is awful. Like don't buy this resin because some printers like the resin here, the resin matters a lot. Like that the machines are simpler in the mechanic part and everything works on the light. The resin quality and the amount of money you spend on the resin matters a lot. There are some resins that are cheap and good, other ones are expensive and awful, and other ones are expensive and really good. So, and the different types, for example, this one is a green, they also state the color because a lot of people use this machine for the model maker, and you can see like also the layer height that people has been using. When we have this will produce one file that we just put on the pen drive, and there is a pen drive connection on the side. So how? print, and you select the file, and you click play, that's it. Like on the manual side of these machines, is the only annoying part is this one. It's cleaning and how you locate your model and how you produce the model. That's the most difficult and annoying part. I have to be honest, like more or less of 4 prints, usually 1 fails. And the bad part is like you only see after half an hour, 1 hour of the start, because the platform is here until it hasn't reached at least the 1-2 centimeters. You're not able to see if it has properly printed or not.
And the bunny did not need any support. The bunny didn't need support.
The bunny, I think I will risk it to print like this. This is just test, like.
I have another question. Is the bed always vertical here? I don't understand.
The bed is like this. So it sits down the platform, hardens, move up, move up, move up, move up, move up.
And only resins supports, right?
That's it. Good. Okay. This machine works exactly the same, but uses another software that is preformed. But it's as for the resin, yeah, it's
What's
highly.
the name of that one?
This is for Formlabs 1. Formlabs 1.
What is the most resilient way to 3D print? So for example, if I want to print like one object which has to be as resilient as possible, so that I can basically stand on it and it doesn't break. What would...
Depends. I have print like pieces for leathers.
Yeah.
If you print wood, strong, with a good design, materials, depends. Like if you want to print the more resilient, it's titanium. Like this is about materials, not about
okay.
like. I know in New York, I was with the research department in the Airbus that produces Autodesk. Airbus aluminum 3D printed.
Oh wow!
So actually, now the new series of the 340. Actually, this is the restroom panel. The splitter, the wall inside is 3D printed aluminum parts. Yeah, but the cost of printing aluminum is.
But is it directly the aluminum printed, or is it like the jewelry that you make the positive, then you cast the negative?
No. You print the aluminum.
You print on the
Yeah. Let me see, because this is the assembly wall.
Did you guys ever think of getting a metal printer?
Do you have 1 million euros?
What?
Do you have 1 million euros?
Right now,
If you want to print things like this, I have printed gold here. This is a manufacturing page for like sending things to print. Like they have like all the materials. Shapeways. I don't know, like this print on demand. They have like all the materials, they have all the technology. So basically you upload your model with constraints and they charge you for the things. For example, I have made jewelry for my girlfriend. Here. Yeah.
What a cute boyfriend.
where are they located? Where are they?
Five.
They have factories in New York and Netherlands.
Netherlands?
What was the bike record?
Huh?
Interesting in the bike record.
Bike what?
There was a folder which said like bike record.
Bike? This?
The bike record.
Sorry, I don't hear you.
I think it was record. It said record.
Rapid.
I don't know, like, this is all my designs. Like,
Oh wow.
I have a basic question. What were the liquids on the first station?
Alcohol. This is all alcohol, both alcohol.
And why is one black and the other one transparent?
It's not black. It's just one is dirty and the other one is no material.
Okay.
It's transparent. Like One is the first bath, so it takes the most of the resin out. The other one is like more transparent because it has less resin, like less dirty things. Usually this one is new and we just use transparent resin so far, but we have like yellow and green color, so it becomes like a dirty pool, the first one.
But it's not like, this is just because there's
from
something
where I
in
see
there.
it, from my
But yeah,
point
but
of
that's just because there is something in, which is like, it's transparent.
Is there like a distributed design 3D metal printer that you
For example, look, this is, for example, the parts are printed like this in SLA printed, but this one is a lot of post-process. It's not printing at set. This actually is aluminum soldered to aluminum, and you need to take the blade, a mechanical blade, to cut it blade, and you need to clean it. You need a lot of post-processing. If you're interested in this, actually Shapeways, they offer in the YouTube channel a lot of like the insights of like industrial, like heavy application of 3D printing. It's interesting, like how they manage like to print titanium, and they have videos like really nice.
Can carbon be printed as well? Carbon can also be printed.
Carbon, full carbon, no. It's impossible to
Right,
print.
right.
Actually, I have a piece that is for tomorrow class that I just, if you want to come to tomorrow class, you can come, but not mandatory for them there. Is I printed like the bicycle stem in carbon fiber. It's PETG with carbon fiber 20%.
Okay.
It's opening this, it's so slow. So this is called generative design. So you don't actually design the part. This is traditional approach. This is the automatically generated approach. This is what you should actually aim for in 3D printing, like complex shapes of really, really optimized the material side. So for example, let me show you.